So chapter 2, atoms and elements. There's an interesting statement from John Dalton. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of sensible magnitude are constituted of a vast number of extremely small particles, or atoms, of matter. This may seem somewhat obvious to us now because it's just been accepted for so long, but this was a really big deal back when John Dalton was alive. So if we think about a piece of graphite, you're writing with your pencil and the lead breaks off. That lead is made out of graphite. Take that piece of lead and you cut it in half, and you take one of the halves and you cut it in half, and you take one of the halves and you cut it in half. How far could you go? Yeah, down to a single atom. So we can't actually do that experimentally, right? Because, just, with a knife or something, you get down to the point where the piece is as wide as the knife and you can't cut it in half anymore, or you can't see it anymore. But this was a thought experiment that people thought about. So it turns out that you would end up eventually with individual carbon atoms. And you get down to that carbon atom and you cannot cut that in half and still have it be carbon. The word atom comes from the Greek word atomos, which means indivisible. So atoms compose all ordinary matter. And if we want to understand matter and how it behaves, we have to understand the atoms. In 1827, Robert Brown looked through a microscope at water-suspended particles that had come from pollen grains. And I'm going to show you a very short video of this, and we'll notice that the particles are moving. This was called Brownian Motion, after Brown. Very short. We don't want to look at the rest of those things. So those pollen grains are jiggling around, right? They're moving. They look like they're alive, don't they? And that's what he originally thought. Well, you see things moving like that, they must be alive. But they were not alive. And so the question was, why are they moving like that? What's causing them to do that? He initially thought they were alive, but then he decided, no, that can't be right. So that was 1827. And again, I'm not going to test you on historical facts. This is not a history of chemistry, but these people's names and the dates do come up. So in 1905, Albert Einstein, you've heard of him, right? He developed a theory that explained this motion. He said it's the result of molecular bombardments of the particles due to the thermal energy of the surrounding water. So basically, water molecules in that liquid that the pollen grains were floating on, those molecules are too small to be seen with that microscope, but those particles are moving and they're hitting the pollen and dust particles. And when they hit the particles, they cause them to move a little bit. So it's a little bit like, say, a graduation ceremony, and they throw beach balls out into the crowd, right? And you hit the beach ball, and it just kind of goes all crazy places, right? So imagine that the beach balls were glow in the dark, and they turned off the lights. So you'd see these beach balls moving, but you wouldn't see the people hitting them. So that's what we're seeing when we look at those pollen grains. We're seeing something that's being battered around, but we can't see what's hitting it. So the existence of atoms was inferred from Brownian motion. If the pollen grains are moving around like that, there must be particles that are hitting them. Does anybody have any questions about that? Perrin, he lived in the late 1800s, early 1900s, conducted some experimental measurements that confirmed Einstein's theory and removed any doubt about the particulate nature of matter. In the 1980s, Bennett and Rohrer at IBM in Switzerland did some work that led to the development of the scanning tunneling microscope, STM. And this is really, really a cool thing. So the way this works, and I've got a couple of videos to show you about this one too. This is video day. They take a tip, it's a very sharp point, like a needle, and they hold this very close to the surface that they're examining, and this needle is moved using a computer, basically a robot. And they pass electric current from the tip of this needle through the object that they're looking at. And that tunneling current is very, very sensitive to how far apart those two objects are. And so by controlling the current, they can cause this needle to move at a fixed distance from the surface. And as it comes along here and there's this bump, to keep the current the same, they move the needle up. And so they can go across. And so basically, they're feeling the surface with this needle. And they raster it, they move it across, back and forth, back and forth, back and forth. And then the computer takes note of how far up and down it had to move the needle. And so you get a picture of sorts of the surface. With this technique, we can get the closest we have to pictures of individual atoms. So this photograph here, well, actually it's not a photograph, it's a digital image produced by STM. Here we have some red things on a blue surface. The red things are iron atoms, individual iron atoms on a copper surface. And with this STM, they're also able to pick up a single atom and move it around and put it down where they want. And so here they've taken iron atoms and spelled out the Japanese kanji characters for atom. So they wrote atom with atoms. You know, scientists have sort of a weird, subtle sort of sense of humor. So there's a couple of videos here that are interesting, that show, I think, give you a better idea of how STM works.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
So with that technique, they can build very, very small electric circuits, because, you know, what's the smallest wire that could possibly be made? Well, it would be 1 atom thick, right? Now that's not actually going to work very well, but you can make little wires, etc., on circuit boards that are just a few atoms thick. That's much smaller than you could make using conventional techniques. Then you can also do stuff like this. This is what might be the world's smallest movie. So all those bumps are atoms. And there are several other movies by IBM available on YouTube. But, you know, we can't spend all day watching movies. So. Yes?
So for some reason I thought I heard that atoms were so small that you couldn't even take a picture of them.
That's correct.
So
what we're doing here, this is not a visual picture. This is a computer saying, okay, my probe is here, it's this far off the surface, and it's in this location, XY. And when I move it 1 increment over, then in order for the current to be the same, I have to move it up 1 increment. And so basically these images are generated by a series of coordinates from that probe.
So you're not looking at the actual physical atom.
Correct.
It's a representation.
It's a representation. It's a valid representation, but atoms are too small to see visually, even with the most powerful optical microscope. Yeah, so that's an excellent question. And so in these pictures, they look kind of like cones, right? Well, are atoms shaped like that? No, atoms are spherical. But the resolution available with this technique is limited. And so that's as close as we can get. But it's really quite incredible that we can position individual atoms and move them around and identify where they are. Does anybody else have any questions? So just to give you an idea of how small those letters are, so here are those kanji characters. If we used letters of that size, we could take all the words in the books of the Library of Congress, which is 35 million books, and if you put them end to end on a shelf, it'd be 840 miles of bookshelf, books standing vertically. If you took all the words in all those books and wrote them using letters the size of those kanji characters, they'd fit in an area of 5 square millimeters. So 1 millimeter, 1/10 of a centimeter, by 5 millimeters. All the words in 35 million books. It's mind-boggling. Very, very small. So atoms are mind-bogglingly small, and yet they are the key to connecting the macroscopic world, which is what we can see with our eyes, and microscopic and submicroscopic world, stuff that we can't see with our eyes, we require a microscope to see. So the atom is the smallest identifiable unit of an element. And I've mentioned before, I think of atoms as being a lot like individual Lego blocks, right? We have the individual Lego blocks, and if you've ever been to Legoland, if you haven't, go online, you can find pictures of it. They've made the wonders of the world out of Legos. And there's the Taj Mahal, and there's Mount Rushmore, and these things are, I'm not sure what the scale is, but the Taj Mahal might be like 20 feet tall. It's built out of Legos. And if you go up close to it, you can see, yeah, it's individual little bricks. But if you back away from it, the resolution gets, lost, and it starts to look like the real thing, right? So atoms are like Lego blocks. There are a limited number of different atoms. There's 91 different elements that occur naturally. So if you look all over the place, you only find 91 different kinds of atoms. There are over 20 synthetic elements, these are man-made, that are not found in nature.